Are we live? Looks like we're live. And my mic seems to be sending out. I've got a live preview. I think we're live. All right. Good Tuesday morning today. And that means it's another time for a little bit of learning Rust. Okay, so where were we last time? I believe that, yep, we made it to chapter 5.3 yesterday. And today we're going to continue with methods with more parameters. Good morning, Everest. Hello again. Welcome to the early morning stream. Or I guess it's, I know that several people who watch live are not actually here in the early morning because you're over in Europe or somewhere that's not, 7 a.m. like it is here. But welcome anyways. All right, so without further ado, I think it's a good time to just start up and continue going. So methods with more parameters. So last time we created a structure, we added a method to it, and this is sort of our ability of doing object programming. And I feel that's a very interesting sort of thing. I have some green screen flickered. Oh, yeah, I see that. That's on... Oh, I'm looking at the delayed preview. Hold on. That's on this side, yes. Did that do it? Looks like it did it. Just a couple inches too far back. The green screen can get out of the way sometimes, so after I'm done the stream, I usually move it back to the back of the room, then I have to reposition it in the morning, and it can be accidentally miss it sometimes. But thank you for letting me know, Everest. Okay, so continuing on, what we were doing previously, we had created a structure which is essentially what in other languages we call objects, and we set up the ability to add a method to it and have that method access its own data using self, which is very similar to this. And now we're going to move on to methods with more parameters. So I'm sort of leaning towards like this is the I think Rust is a functional language, or it can be a functional language. I can't remember which one it sort of like is solidly in. But so far it's feeling much more functional language. Like we're creating objects without classes, but we can create them using everything we want, and we just don't have to worry, at least so far, about any kind of extensions or oh, what is it called? I always forget the words for object-oriented programming. Basically, the inheritance problems that come with object-oriented programming. So far, it doesn't look like we're gonna have to deal with those, which is nice. With that, methods with more parameters. Let's practice using methods by implementing a second method on the rectangle struct. This time we want an instance of rectangle to take another instance of rectangle and return true. If the second rectangle can fit completely within self, otherwise it should return false. That is, we want to be able to write a program shown in listing 514 once we've defined the canHold method. So it sounds... This is a classic problem in gaming where it's like, oh, let's do collision detection, but we want to like catch it completely or check to see if like the right side is, or in this case, the complete thing is inside of another object. Okay, so looks like we're going to create 3 of our rectangles from this. And we're going to create a can hold and pass it a reference to each of the rectangles. And then we're going to decide, oh, hey, does it exist? So in this case, we're only doing width. So we're just saying like, hey, are you big enough that you could hold this rectangle? And I think I can just implement this right now. So let's come over here. Let's go into our rectangles and open up code. Okay, so the idea of what we want to do here and I'm thinking today I'm going to try bringing you over here and you over here. So that way I don't have to worry about it potentially me getting in the way of this code. Later. Okay, so we have our rectangle. It's going to have this height and width. We have this sort of method that's defined onto it. What we really want to do now is we have height 30 and 50. And what we have 30 and 50, 10 and 40, 60 and 45 is the next 2 that they want us to do. So let's do that. So let we'll do rect2 equals rectangle, and we're gonna get height is 10 and width is 40, and let rect3 equals rectangle, and this is going to be height of, what was this last one again? 60 and 45. So height is 60, width is 45. So once we have these, now we have these 2 print lines. I'm not really caring about them, so I'm going to let them be commented out. But we're going to put in print line so like maybe the name of the rectangle. So I kind of, hey Felix, welcome to the stream. I kind of want to add in here a name, and we're gonna do what should I do in here? I think, didn't they suggested that we don't put in actual like borrowed values, but we put in full strings, so like that. And now as I create a rectangle, which I'm going to put this on one line as well. Although this is going to make it not as easy to do. So if I do rect1, name is, and it's going to be string from, oh yeah, that's ugly. Everybody go home. Oh, home up 1, copy down. Hey, that works with multi-cursors. Let's see if I remember properly how to create an actual true string here and throw it into rectangle. And now with a print line, I can now say sort of string one. So the name can fit inside rect inside it. Boom. Okay, so what are we going to put inside of here? Well, it's going to be the name of the first one. So like rect2, rect3 can fit inside of rect1. So we'll do rect2.name, and then this is going to be rect1.name, and then can fit inside of this. So it's rect1 dot can fit inside, and a reference to rect2. Now, of course, it's going to yell at me because I don't have this method, but we can do that. Function can fit inside, and this takes in a reference to self. And I don't think I need to take anything. Oh no, I do need to take something else in. So it's going to take a reference to self. It's also going to take a reference to a, I think it's reference rect, which is type rectangle. And it's going to return a bool like that. And expected struct rectangle found reference. Is that because expected struct rectangle found reference to rectangle? Sort of expecting that I could pass a reference to it in and catch it as a reference. Or do I have to say that this is type? Like this is a type reference? Like that? Oh yeah, apparently. And yeah, no return value yet. So we can do that. So I have to actually convert it. Oh, I put the reference over here. So I go like that. Right. The name, this is just the name of the variable coming in, and this is the type. Perfect. Thank you, Felix. Okay, so we have can fit inside, and all we want to do is see is the width and height less than. So can I just do this all in one line and say and self, I guess it's just self dot height is less than, actually it's not self dot height, it is rect dot height is less than self dot height, and rect dot width is less than self dot width. So this is working. Area is, oh, method is never used. Well, that's because I commented out all the code. So I'm not really concerned about that. Okay, so now if I run you, you should tell me if that works. Let's save you and cargo run. Rect2 can fit inside of rect1. True, exactly what we wanted, because rect1 is 30 by 50 and this is 10 by 40. And so then 3 should not be able to fit inside of 4. And maybe what I do want to do is let area equals calculate area of my rectangle. I don't need this anymore. It's just going to be self. Oh wait, it's not area equals calculate area. I don't think I want that one anymore. It's this one right here. So the area, this one. The area of is, so it's going to be rect1 dot name, and then rect1 dot area, and I called it area, and we're not going to pass it in hello world. That's silly. All right, so that should give us a little bit better output. That's too low. Could not compile rectangles. Print line not found. Where did I leave that in? Oh, I left a print line in here. All this experimentation that I don't remember doing. Although I kind of do remember doing it. All right, the area of rect1 is 1500. Rect2 can fit inside of rect1. True. So let's do the exact same thing for rect2. Should be a little bit easier now. Apparently, I don't know how to duplicate a line keystroke, so I'll just do the old-fashioned way. Okay, so this will be rect3. Can fit inside of rect1. Rect1 can fit inside rect3. By the way, if you want to suppress warnings about unused functions for the whole file, you can put, and it's, okay, so this is this a trait? Because I believe it was, like, we're adding a trait to the structure. And so is this adding a trait to the entire file? So if I do that, well, now it doesn't matter because I don't have any dead code. I guess I could create function unused that takes in self, returns bool, and we'll just say true. Yeah, so now I'm not getting the error there. So that's awesome. Thank you, Avers. Okay, so I've got all of this set up. Save the file. Let's run this again. And area of rect1 is 1500. Rect2 can fit inside of rect1. True. Rect3 can fit inside of rect1. False. Perfect. Let's go back to the book. That book. Okay, so, and the expected output would look like the following, because both dimensions of rect2 are smaller than the dimensions of rect1, but rect3 is wider than rect1. Okay, so the hash square brackets is a compiler annotation. For example, derive is an annotation. Derive is for the containing module without the bang for the next item. Oh, it's okay. So there's just more. Basically, it feels to me then that if this, because it's such a simple code, but yeah, I do notice now. I didn't notice at the beginning that this one didn't have the bang on it. So yeah, okay, I see. Allow, derive. It feels a little bit overloaded because it's being used in like a different way, but at the same time, it's telling the compiler to do stuff. So it'll be interesting to sort of learn more about these. I wonder if there's going to be a part in the book for that. Thank you, both of you, for that information. Okay, so we got the can hold rect, true, true. We know we want to define a method, so it would be within the implied rectangle block. The method name will be can hold, and it will take an immutable borrow of another rectangle as a parameter. We can tell what the type of the parameter will be by looking at the code that calls the method. rect1 can hold rect2, passes in rect2, which is immutable borrow to rect2. An instance of rectangle. This makes sense because we only need to read rect2 rather than write, which would mean we'd need to immutable borrow, and we want main to retain ownership of rect2 so we can use it again after calling the canHold method. The return value of canHold will be a Boolean, and the implementation will check whether the width and height of self are both greater than the width and height of the other rectangle. All right, so we've already done that. Let's take a look at how they did it. Here's a canHold. They take in reference to self. They called it other, and reference to rectangle. Return a bool, self width. So it feels like they did exactly the same thing I did, except they just reversed the other way around, so they can do less than, and I did greater than. The bang just sets it for the whole file. You can annotate single functions with allow dead code, similar to the example Felix just gave. Oh, interesting. So the bang does the entire file. Interesting. Well, I am going to look forward to when, hopefully the book will fully introduce that. I'll be able to play around with it a lot more. When we run this code with the main function and listing 514, we'll get our desired output. Methods can take multiple parameters that we add to the signature after the self parameter, and those parameters work just like parameters in functions. Associated functions. Another useful feature of the implement block is that we're allowed to define functions within implement blocks that don't take self as a parameter. These are called associated functions because they're associated with the struct. They're still functions, not methods, because they don't have an instance of the struct to work with. You've already used the string from associated function. Associated functions are often used for constructors that will return a new instance of the struct. For example, we could provide an associated function that would have one dimension parameter and use that as both width and height, thus making it easier to create a square rectangle rather than having to specify the same value twice. Okay, so creating a square, it takes in a size, U32 returns a new rectangle, and then just returns rectangle width. Oh, interesting, okay. To call this associated function, we use the : syntax with the struct name, like let a square equals rectangles : square 3. For example, this function is namespaced by the struct. The : syntax is used for both associated functions and namespaces created by modules, which we'll discuss in chapter 7. All right, so let's try implementing that as well. So we have our unused. I'm going to leave that alone. We're going to do function, maybe like create a square, and it's going to take in a size, which is a U32, and we're going to return a full rectangle. So to give ownership to whoever's calling it. What are you yelling about? You're not. You're yelling that I didn't return something. So we take this and we're going to return rectangle with a oh, because I don't have a name on here? That's interesting. So the way I've done it, I also need to take in a name, which is a, let's see. This is going to be a string or a borrow. Do I care? It can be a reference. Could be a borrow of a string. We're going to take a rectangle. We're going to return sort of name, except I can't really do that. I don't want to put it like a full borrow in. I do want to have a string from name, like that. And then I'm gonna have width is gonna be size, height is gonna be size. Nope, no semicolon. All right, no errors coming in there. Let's create a new square down here and just print it out, which I can do because I have this derive debug on here. So maybe below all of this, we're gonna say let my square equals rectangle create oh, nice, it found it already. Oh, nice, and it found like what exactly I need to put in here and sort of set that up for me. So that's a nice thing that that code is doing for me. So size, we can just do this as 32, why not? Name is going to be my square. And then we're gonna print line has size. Can I do this now? So I'm gonna do colon question mark. So it's gonna be, actually, that doesn't really make sense. I'll just do this. And it's gonna be my square. Save that, and now I should be able to run cargo run. Rectangle, name my square, height 32, width 32. Perfect, worked exactly as we wanted it to. So that's the associated function we created. Let's move down. Multiple implementation blocks. Each struct is allowed to have multiple implementation blocks. For example, listing 515 is equivalent to the code shown in listing 516, which has each method in its own implementation block. Okay, so yeah, implement rectangle, function array, implement rectangle can hold. There's no reason to separate these methods into multiple implementation blocks here, but it's valid syntax. We will see a case when multiple implementation blocks are useful in chapter 10 when we discuss generic types and traits. So I wonder, I haven't seen any like Rust code in the wild. So I sort of like feel that if you're creating a structure, everything should be related to each other at that point, and you wouldn't necessarily have like the need for separate implementation blocks because you want to like have everything that's related to each other right there together. Unless maybe you want to put all of the associated functions in one and then put all of the non-associated functions in another. But you can't name the implementation block, which is where I would potentially do that. So I don't know. They're sort of hinting that the best use for this is to not do multiple implementation blocks, except in this case, which we'll learn about later. All right. Summary. Structs let us create custom types that are meaningful for our domain. By using structs, we can keep associated pieces of data connected to each other and name each piece to make our code clear. Methods let us specify the behavior that instances of our structs have. And associated functions let us namespace functionality that is particular to our struct without having an instance available. But structs aren't the only way we can create custom types. Let's return to Rust's enum feature to add another tool to our toolbox. All right, so with that, we are done with chapter 5. And now we get to move on to enums and pattern matching. Okay, in this chapter, we'll look at enumerations, also referred to as enums. Enums allow you to define a type by enumerating its possible values. First, we'll define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that a value can be either something or nothing. Then we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. Finally, we'll cover how the if-let construct is another convenient and concise idiom available to you to handle enums in your code. So that's kind of funny because when I was in, chapter 3, I had started doing like the code of my own, and I kind of went off the rails a little bit, wanting to jump into functions before they had shown us how to use them. And so I started using if-let by accident because I just went online to look about if, and that's what I saw. And yes, well, that's if definitely has its own thing, and if-let itself, we're looking forward to learning how it actually works and not just causing errors in my code. Enums are a feature in many languages, but their capabilities differ in each language. Rust enums are most similar to algebraic data types in functional languages like F#, OCaml, and Haskell. So I've not used any of those languages, so this will be an adventure. Let's move on to chapter 6.1, defining an enum. Let's look at a situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with IP addresses. Currently, 2 major standards are used for IP addresses, version 4 and version 6. These are the only possibilities for an IP address that our program will come across. We can enumerate all possible values, which is where enumeration gets its name. Any IP address can be either a version 4 or a version 6 address, but not both at the same time. That property of IP addresses makes the enum data structure appropriate for this case, because enum values can only be one of the variants. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type when the code is handling situations that apply to any kind of IP address. We can express this concept in code by defining an IP address kind enumeration and listing the possible kinds of IP addresses an IP address can be, version 4 and version 6. These are known as the variants of an enum. Okay, so we're creating enum, IP address kind, and then we're just defining v4 and v6. What's interesting is that these are just on its own. Oh, okay. So IP address kind is now a custom data type that we can use elsewhere in our code. Enum values. We can create instances of each of the 2 variants of IP address kind like this. Let 4 equals IP address kind : v4. Let 6 equals IP address kind : v6. Note that the variants of the enum are namespaced under its identifier, and we use a double colon to separate the 2. The reason this is useful is that now both values, IP address kind v4 and IP address kind v6, are of the same type, IP address kind. We can then, for instance, define a function that takes any IP address kind. Okay. Now we're not like actually assigning values into these. We're just sort of like setting what they are. But we're using the equal sign Okay, so moving on. With either variant, okay. Using enums has even more advantages. Thinking more about our IP address type, at the moment we don't have a way to store the actual IP address data, we only know what kind it is. Given that you just learned about structs in Chapter 5, you might tackle this problem as shown in listing 6.1. So we have our enum, IP address kind, v4 v6. We have a structure of IP address. Kind is IP address kind. Okay, so we're going to set like the kind as a v4 or v6 and address is string. I feel that there's definitely going to be a better way. I think they're leading us up to that. Yeah, that's sort of what I feel. Here we've defined a struct IP address that has two fields, a kind field that is of type IP address kind, the enum we defined previously, and an address field of type string. We have two instances of this struct. The first, home, has the value IP address kind v4 as its kind, with associated address data of 127.0.0.1. The second instance, loopback, has the other variant of IP address kind as its kind value, v6, and has address 1 associated with it. We've used a struct to bundle the kind and address values together, so now the variant is associated with the value. We can represent the same concept in a more concise way using just an enum rather than an enum inside a struct by putting data directly into each enum variant. This new definition of the IP address enum says that both v4 and v6 variants will have an associated string values. Yeah, I was kind of hoping that they would allow us to do something like this. So yeah, we create the enum IP address. We say like you're gonna have v4 and it's gonna be type string. So that's nice. Okay, and so we use IP address : v4 parentheses, sort of like a function, and then pass in the data. That's interesting. We attach data to each variant of the enum directly, so there is no need for an extra struct. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. Version 4 type IP addresses will always have 4 numeric components that will have values between 0 and 255. If we wanted to store v4 addresses as 4 U8 values, but still express v6 addresses as one string value, we wouldn't be able to with a struct. Enums handle this case with ease. Oh yeah, because we'd be able to say like, oh, the v4 is going to look like this, the v6 is going to look like this. Yeah, okay, I see what they're doing here. So v4 is going to take these 4 8-bit numbers, unsigned 8-bit integers, just like that. And now we can do whatever we want with them. We've shown several different possibilities that we could define in our code for storing IP addresses of the two different varieties using an enum. However, as it turns out, wanting to store IP addresses and encode which kind they are is so common that the standard library has a definition we can use. Let's look at how the standard library defines IP address. It has the exact enum and variants that we've defined and used, but it embeds the address data inside the variants in the form of two different structs, which are defined differently for each variant. Okay, so we have struct IP address, struct IP6 address, and our enum IP address. Okay, so I was kind of wondering about this, which is that, like previously they showed us an enum inside of a struct, but I kind of feel that it might be better to have an enum that holds structs, because the struct is a really great way of storing this, especially complicated data together. So I kind of like this method a lot more. This code illustrates that you can put any kind of data inside an enum variant, strings, numeric types, or structs. For example, you can even include another enum. Also, standard library types are often not much more complicated than what you might come up with. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope. Okay, yeah, so we can just, but if we brought it into the scope, everybody, the compiler will have a fit. We'll talk more about bringing types into scope in Chapter 7. Let's look at another example of an enum in Lysine 6.2. This one has a wide variety of types. So enum message, so quit, which doesn't have like a type associated with it, move and an x and y coordinates, write, a string, change color,